Okay, so I'm here and I lied. You remember what I told you on Monday? So GC will start today with Gary. Okay, I lied. I wanted to finish the lecture, so I told Gary to come on Friday instead. So I wanted to finish this whole principle of chromatography before he starts his GC section. Because if I come back to it next week, everything will be chaotic and lost. All right, let's review a little bit of what we talked about last time. What is peak resolution? So, Millie. How well your Yes, exactly. Resolute from each other, separate from each other. Yes. So peak resolution is separating of those individual solutes from each other, and the peak represent an individual solute most of the time, unless there is coelution. What is the first step in developing a separation? What's the very first thing you do when you have to separate and yeah, you look at references. We talked a little bit about that. Everything that you encounter, most likely somebody else tackled. So you look at references, see what's available in literature, and see what fits better with your lab, what can be adjusted. Then you test it to see how you need to modify it to suit your equipment. Okay. What is a solvent front peak? Say that again. It's not the first detection of this. It's the first detection of the mobile phase reaching the detector. So, and oftentimes we use it to calculate both volume. So this is the mobile phase from the minute of injection to reaching the detector. The detector goes, oh, something hit me. That's the solvent front or solvent peak or void volume peak. Okay. What is the difference between retention volume and retention time? What is retention? When we say retention, what do we mean by retention? Retention of what? You know this, all of you. Talk to me. There are no cockroaches today. I think not Nigel. No cockroaches. Were you not here last? It's okay. I think Nigel, well, not I think Nigel called emailed facilities, so I hope they came and did some measure there. Okay, so I don't know what is my question. Okay, so what are we? The rotation of your solute. Yeah, on the column, on the stationary phase. So when we say retention volume, we mean the volume of the mobile phase it took to get that solute out. So did it take 10 milliliter? Did it take 20 milliliters to get that solute off of the column from the time of injection? So retention time is associated with retention volume. So instead of measuring the volume, you measure the time it took from the second of injection to the compound reaching the detector. When it reaches the detector, the time is recorded, and that's your retention time. And often, or all the time, so you're going to see me draw this very often. So you'll have this is your solvent front. It depends if it's a GC. Sometimes it's much bigger than this. HPLC is tiny. And then you have your compound coming off the column. And this is here time. And this here what? I drew this before. So what's here? What's the y-axis?
Signal strength.
Yes. So area under the peak we calculated here. So here we measure signal. Yeah. So the signal in HPLC was absorption because we're measuring absorption. In GC, we were measuring flame ionization detector. So it was the ionization change in the signal due to ionization. Okay, so the retention time, usually we get it right in the middle of the peak. So here we record the retention time. So whatever it is, let's say it's 7.2 minutes. That's your retention time at the peak, the highest concentration of your sample. Okay. Yes.
Would there be problems if the solvent you have for your sample is the same as your mobile phase?
You want the solvent that you have your sample competitive. What's
If-
the word? Huh?
But if it's the same, would you have,
Compatible, yes. Huh?
but if your solvent is the same,
As the mobile phase, that's fine.
then you won't get a solvent peak,
You
'Cause you
will
won't
always will get a solvent peak.
even if your solvent's the same as in your mobile phase.
Yes. From the time of injection to the time of reaching the detector, the mobile, because the sample when you inject 20 microliter, 40 microliter, that's in
Yeah.
LC. In GC, it's even much smaller. So it's insignificant. What's significant is the mobile phase that is flowing at a particular rate.
And I'm wondering in LC, if the solvent and the mobile phase are the same, would that ever happen? Like if you're doing hexane, a sample dissolved in hexane, and hexane is your mobile phase.
So will we not see a solvent peak? Is that what you're saying? Well, I don't know. I'm assuming you should because detection starts when you hit the injection.
Yeah.
So I'll have to think about it. I'll come back to you. This is a very specific question. I have to think about it.
In OChem, that was what we did. So we never even, for just column chromatography. It was hexane and hexane.
So there was no solvent peak.
But we weren't worried about that then. So that's why I'm.
Okay. Well, I need to think about it. It makes sense, but let me think about it. I don't want to answer anything wrong. Okay. What is the relationship of peak width to resolution? We have not covered this yet, but
Is it the narrow?
yeah, exactly. Probably I covered it. I don't know, but that is correct. So and I'll draw this many times, when your sample is here, injected on the column, it starts going through by diffusion, but also it can move in and out to get an equilibrium between the stationary phase and the mobile phase. So it kind of gets, I'm going to talk about number of theoretical plates. It has multiple equilibriums that happen. And the peak width is really proportional to this equilibrium. So if you have a lot of diffusion, if the sample diffuses over like this area, the peak widens. Because now it takes longer time to come out because it's diffused. So it takes really longer time for all of the molecule to come out, all of the solute to come out, multiple molecules, all of the solute to come out. So instead of coming out in a span of 1 minute, it might come out in a span of 2 minutes. So then your width changes. If you had another peak here, then you see this coelution happening and you lose resolution. Because now, instead of having two sharp peaks, they widen, they diffused inside of the column more than move with the mobile phase. And that diffusion made them spread and come out over an extended period of time. So this is important to understand because it helps you understand the next things I'm going to talk about. Does anybody want me to repeat this one? Do we understand what happens if the solute spreads throughout the stationary phase instead of move with the mobile phase and reach equilibrium fast? if they don't reach equilibrium fast and they are diffusing within the stationary phase, they kind of spread, and take longer time to come out of them. Right, so this is important for us to continue our conversation, which leads me to this resolution of two peaks. So the resolution of two peaks is what you see there. RS stands for resolution. It is 2 into delta T, which is the difference in retention time of the two peaks. Peak number 2 and peak number 1. So the difference in retention time by the width of the peak 2 and peak 1. So inversely proportional to the width. The resolution is inversely proportional to the width. If the width widens, like in this example, you lose resolution and resolution decreases. So it's inversely proportional to the width. Okay, so that explains this phenomenon. You have good separation, and for some reason, we'll talk about the reasons, we don't reach equilibrium quickly, sample diffuses, then it takes longer to come out, then the two peaks that used to be resolved co-elute or no longer resolve. So the width is wider and hence the inverse relationship. Okay. Good so far? All right. Resolution is a function of three things. Now things are going to get a little bit more intense. I'm going to talk about those functions: efficiency, selectivity, and capacity. So I'll explain each one separately, and then everything will come together at the end. So what does N stands for? I just mentioned it a moment ago. N, number of theoretical plates. So efficiency is related to number of theoretical plates. I'll explain this in a minute. What is number of theoretical plates? Alpha is the separation coefficient between two peaks. So the more separation I have, the better selectivity. So my stationary phase is selective to these individual components so that they can separate. And then capacity, how much capacity the column have, how much functional groups the stationary phase have to allow interaction with the solute. Okay, so efficiency, selectivity, capacity, and we're going to talk about each one of those separately. Okay, so number of theoretical plates. Let me redraw this. So the stationary phase in the column is theoretically divided into sections. And N is the number of sections. So here I have 1, 2, 3, 4, 5. Imaginary sections. What are these sections? The column is not really divided, but every compound, when it comes in, and you're starting with a very new column, very efficient, you haven't worked with it yet, you didn't damage your column, so maximum efficiency. So when you inject your sample with the solutes, if the column is efficient, stationary phase is new, you expect you get equilibrium. Yeah, right? equilibrium quickly between mobile phase as it moves through your column. You have a pump, pumps the mobile phase through the column and carry your constituents. So you will get an equilibrium between the stationary phase and mobile phase. So the molecule or the solute reaches an equilibrium fast. You have high efficiency. So these segments are equilibrium segments. The more segments you have, the sharper is your peak. Sharp. Better, most likely better resolution. So that's number of theoretical. Over time, you exhaust the column, you exhaust the stationary phase, you lose components of the column, some of the particles are lost over time, then your equilibrium takes longer. So we go from this to 1, 2, 3. Now n equal 3 versus n equal 5. So what happened? It took longer to reach equilibrium. So now I have a wider peak. So over time, when the stationary phase appreciates, number of theoretical plays goes down. Okay, so you have harder time reaching equilibrium, takes longer time. Your solute diffuses within the column, and then it takes longer time for it, all of it, to leave the column, and that will impact resolution. All right, questions? Okay. Yeah. So these are theoretical, right? So we don't see them by the eye, it's not a segment. And they are dependent on the column length. Why are they dependent on the column length? Why do you think? Okay, good.
The longer the column, the more you have.
The longer the column, the more you have. Okay, so the length of the column is going to impact my calculation of the efficiency of the column. Two columns might have the same efficiency, but one is longer. How do I correct for that? We calculate something called height equivalent of a theoretical plate. It's coming on the next slide. Height equivalent of a theoretical plate. So instead of counting the theoretical plate, we just take the height. And now we have corrected for the length of the column. No matter how long the column is, all I care for is did it widen or not? So the height equivalent of a theoretical plate. That's one thing coming on the next slide. And one other thing you see here in red varies with the type of solutes. So it's not the same. N equal 5 is not the same for caffeine and the same for isoflavone, for example. It's not the same because they interact differently with the column. They reach equilibrium at different times. So for every molecule or solute, you have a different theoretical plate, number of theoretical plates, and height equivalent of theoretical plate. This is very important. If you work in the future with a column and you want to test its efficiency, when you get the column, you run through it a sample, a standard, caffeine, glucose, whatever it is. You run through it, calculate number of theoretical plate and height equivalent of theoretical plate. After 6 months, you run the same standard. And then if number of theoretical plate and height equivalent of theoretical plate changes, that means your efficiency of the column changed. So it cannot be the same for all molecules, all compounds. All right, so height equivalent of a theoretical plate. Bear with me. We go this way. So what you see here, you see A, that's gonna call it eddy diffusion. B, longitudinal diffusion. And then C, transfer factor. And then the mu is flow rate. Well, let me explain each one of those, walk you through them slowly. All right, so you have a river of water. And then in the river, you have very, very, very small pebbles. But in certain section of the river, we have big rocks. Okay. So this is a river. And then you have small pebbles. And then somewhere you have big rocks. So your mobile phase, the water, is going through over small pebbles. Whereas when it comes here, there will be much more routes to go over. So now the compound solute diffused more into my circular phase because the mobile phase had so many routes to go to come back to here. So a lot of diffusion and delay to get to your equilibrium. So what does this tell us? The smaller the particle size they use to pack their column the better. So usually your stationary phase should have very, very fine, small particles to avoid eddy diffusion being great. Because with high eddy diffusion, your height equivalent of theoretical plate goes up. So the equation is proportional to A. The higher A, the higher is the height equivalent of theoretical plate, the lower is your efficiency. What is this again? Longitudinal. Longitudinal. I don't know, did I not spell it right? Longitudinal diffusion. Okay, so A we figured. Now longitudinal diffusion happens all the time. When you go from a concentration, high concentration to low concentration, it diffuses. So there is diffusion that always is happening from this point to this point. So there is in and out, but there's also diffusion, longitudinal LD, longitudinal diffusion always happening. So this is greatly impacted by the flow rate of your mobile phone. Let's say you have 1 ml per minute versus 0.1 ml per minute. Which one will cause more longitudinal diffusion? The 1 ml or the 0.1? Which one will cause your solutes to just travel within the stationary phase rather than in and out? The 0.1? Yes, absolutely. The slower your flow rate, the more problematic it's going to be, and you'll have more diffusion in the column, wider peaks. Then when your flow rate is higher, you can reach equilibrium faster. However, too high of a flow rate, you will not have good resolution. Your peaks will come too close to each other. At the very beginning early, 0 to 10 minutes. And then they might all show up as one peak. If the flow rate is so high, you won't be able to control the separation because everybody's starting to move too fast and not enough to reach equilibrium. So that's why the rate here, U, has two impacts. Too high is not good, too slow is not. Too slow is gonna cause diffusion within the column. Too high, you don't reach equilibrium. You will get all of them coming out very fast, leaving the column. So that's why we always try to control the flow rate to get to that sweet spot. And then the last one is transfer factor. It's impacted a lot by the flow rate. So transfer factor is related to going in and out. So transfer, which is C, I'll draw it here. So transfer, meaning moving in and out of the stationary phase into the mobile phase, the compound or the solute. So too high, well, too slow, then you don't have enough transfer. Too high, you don't get equilibrium. So you want also a flow rate that allows fast movement, fast equilibrium, but not too fast. Because too fast will cause correlation. So Gary is going to talk about capillary columns in GC. Sometimes in HPLC we use capillary columns too. What are capillary columns? So these columns are hollow and you have stationary phase, just a thin layer inside of the column as stationary phase. So when you don't have a lot of material, your C factor is very good. You have very quick equilibrium, very, very sharp peaks. In GC, you really see sharp peaks. In HPLC, the peaks are a little wider. Because capillary column helps. So the compounds going in don't have a lot of room to go into the stationary phase and be lost. Because you have a very thin layer, so you reach equilibrium very quickly. Also, we'll talk when we cover HPLC, we'll talk about those micro tubes, HPLC. So the narrower the column, the better is the resolution. So narrow and long, better resolution. Because then you don't have a lot of stationary phase for the compound to just go in and get lost and diffuse and all of that. So the narrower the column, or if you use capillary column, the better is the transfer factor, or the smaller it is. You need smaller transfer factor to have a smaller height. So you have a smaller transfer factor. Okay, did I lose most of you? You can ask questions. Yes.
We'll just propose it. Well, the separation you need of one of these micro capillary things that's a meter long, how big would you need if it was 5 inches?
So the size, if you have a lot of compounds that are very similar in their molecular structure, if you have a short column, you don't give them enough time to separate.
I mean, like if you wanted the same separation with a capillary column as you have a 5-inch column, probably with that, like thousands of. Don't worry. The 5-inch will never.
So you choose the size, the dimension of the column based on the separation you need to get. Okay, sometimes a short column and you have a very complex mixture will not be enough, so will not be suitable for the separation that you want. We can talk more about it later. But okay, so temperature is important because sometimes we increase the temperature, like those of you that did HPLC, we ran it, was it at 35 degrees C? Can't remember, but little elevated over the room temperature. That helps with reaching equilibrium faster and with the transfer factor. So the transfer factor becomes smaller at higher temperature, helps reducing the height equivalent of theoretical plate. So basically, this figure shows you that there is really, you have to manipulate your conditions, whether it is flow rate, the column dimension, the thickness of your stationary phase, temperature, and flow rate to reach the smallest height equivalent theoretical plate that needs to be given. That would be the target. On the y-axis is the height equivalent of theoretical plate. So you want to reach here, this. And then at this point, you will have a unique flow rate, temperature, characteristics of the column that allows you to have maximum efficiency. So selectivity is easier to think about. So the more selective your stationary phase is to your compounds of interest, the better separation you're going to get. If you have compounds that are very similar in molecular structure and your stationary phase is not able to select them properly or have good selectivity, then we don't get separation. So usually this is controlled by our choice of stationary phase and our choice of mobile phase. So the selectivity is something that we can control by selecting the stationary phase and the mobile phase based on the characteristics of our compounds. And it has more impact on resolution than the efficiency. So if you don't have good selectivity, your resolution will be poor. So it has more weight because here it's 1/4 of the number of theoretical plate has an impact on resolution. Last factor is capacity. This, you want to think about your stationary phase having a lot of particles, and each particle have functional groups on it where your compounds are interacting. The more you run your column and you run mobile phase over mobile phase and many injections, you lose particles in the column. And functional groups get blocked, maybe, especially protein, working protein, they foul your column. So they block the functional groups. So you lose capacity over time. So this is where sometimes you can fix it. Sometimes you say, okay, I'm gonna throw away my column and get new media or buy a new column. So when you lose functional groups, you have less interaction with the column. Remember, chromatography is about first interacting with your stationary phase. If you lose interaction with the stationary phase, they will come out quicker. So A, instead of coming out at 10 minutes, will come out at 7 minutes. And if there was another compound coming out at 5 minutes, they're going to coagulate. So they will stay less on the column, they will have more coelution. So that's what capacity means. We lose capacity over time, and they will interact less with the stationary phase. Okay. Going on to qualitative, quantitative analysis. So when we run chromatography, we want to separate for certain purposes. One, qualitative. Is a compound there or not? So detect. And then sometimes we want to identify. So we detect the contaminant, we need to know what it is. So that's all qualitative. Detect, identify. And how do we detect and identify? Sometimes we compare retention time and standard of the sample to retention time of standard. Then we say, okay, this is caffeine. It seems like it's coming out at the time of the standard caffeine coming out. Sometimes we spike the sample. So let me show you again. So you're running a sample and you have 3 peaks that are coming close to each other around the same time a standard comes out, and we don't know which is which. So I spike it. Let's say this is my caffeine. I spike it. So it means I put a little bit of caffeine in my sample, and then I'll see that this peak got bigger. Then I'll know which one is which. Photodiode array detector, we'll talk about it when we cover spectroscopy, but some of you also saw it in lab. It allows you to give fingerprint of a compound, absorption fingerprint, a spectra. So the spectra is unique most of the cases to this compound. So you get a spectra. So here you have wave length, call it lambda. And then here is your signal, absorption or whatever. It gives you a signal at every wavelength. So this is unique fingerprint to a particular compound. So oftentimes we can tell compounds apart based on their absorption fingerprint, wave, light absorption fingerprint. Sometimes we put multiple detectors in a row. Like it happens a lot with GC, for example, and LC. So you have the first detector, let's say it's a GC FID, flame ionization detector, and then you put an MS. So you enhance detection sensitivity and selectivity. Peak ratio. So if you have two compounds that have the same signal, let's say we're measuring at 282, same wavelength of the caffeine standard. And then you have two compounds co-eluting, they absorb at the same wavelength. Then you measure at 254 and take the ratio of the signal at 254 to 2282. And you will notice that it's different, so you can differentiate between two compounds. And sometimes if you have two compounds coming together at the same time, let's say this is size exclusion chromatography. Two proteins having the same size, but they're different. Then I do size exclusion, then I do ion exchange to separate them based on charge. So 2D separation, 3D separation sometimes. And then mass spectrometry help us identify based on molecular weight and ion characterization. So that's a stronger qualitative method of analysis. But often, especially in food analysis, we need to quantitate. And that's where we do get the area under the curve. So it used, in the olden days, they used to have a recorder, strip chart recorder, and then you take it, you cut the peak and you weigh the peak. But now we have programs that would calculate the area under the curve, and we relate the area under the curve to the concentration of the standards. And we have area under the curve as y-axis and known concentration of standards as x-axis. And you get equation of the line. So you prepare 4 or 5 different concentrations like you did in the caffeine lab. And then you measure the area under the curve, or the computer generates the area under the curve, and you plot, you get equation of the line, and then you calculate concentration in the unknown based on its absorption. Very easy. Sorry, that's my sensor. Very easy, external standard. Now I'm gonna tell you in the last few minutes the difference between external and internal standards. And I have another slide. I will post that on Canvas, but oh, So here I differentiate between external and internal sample. If you want to quantify with maximum accuracy, if you have a very tedious sample preparation, you need both external and internal. You cannot quantify without an external standard because the external standard, you have to use it to plot standard code. Okay, so external standard is important for quantification. Internal standard is important to correct for any sample preparation error. So internal standards, you add it to all of your standards. External standard. Let's say you are doing sugar, I'll give you a sugar example, glucose, fructose, sucrose, and then you get lactose as an internal standard. You add lactose to all of your standards, like glucose standards, the fructose standard, the sucrose standard, and then you add it also to yourself in the same amount. So everybody got the same internal standard. So your internal standard should be added at the exact same concentration. You can control that concentration. It should be structurally similar to glucose, fructose, and sucrose, whatever you're analyzing, so that it shows up in your chromatogram. So it's not, if it's too different, it won't be separated using your stationary phase and mobile. So be structurally similar, but should not co-elude, should not come out with any of your sample components. And it should be within the analysis time. If analysis time is 10 minutes, shouldn't come out at 20 minutes, it should come out within your analysis time. So, and it's used to correct for variability that is due to sample prep, your dilution, your weighing, any experimental error. The standards, those internal standards will be subjected to the same errors. The external standard is, so the external standards is the same component you're measuring. So caffeine in your sample, you get the caffeine standard. Glucose, you get a glucose standard. And you prepare them at different concentration. And these, you use this to generate your standard curve for quantification. So can you quantify without external standards? No. Can you be super accurate without an internal standard? No, especially if you have tedious sample preparation. So each one of those has specific function. You cannot just use internal standard and then quantitate. No. Okay, so you need both to quantitate and if you want to enhance accuracy. Sometimes sample preparation is easy, you don't need an internal standard. Okay, so to visualize. So we want to determine different sugar components in molasses, and we used lactose because lactose is a sugar from milk. It's not in molasses, and it will come out in the same analysis time. So we prepare standards of fructose, glucose, and sucrose, different concentrations here. And this red drop is a known concentration of lactose. It goes in all of your standards and in your sample. Okay. Then you will run your glucose standards, fructose and lactose, and glucose and sucrose. And then you will have the internal lactose standard, same area under the curve or similar. And when you plot your standard curves, you take the ratio of glucose area over lactose area, the ratio of fructose over lactose, the ratio of sucrose over lactose. And you plot a standard curve for each one of them. So you will have 3 different standard curves, and you are all of them accounting for the internal standard. So you will use this equation of the line for each one of them. Let's say you have glucose. This is your sample chromatogram. You take the area of glucose and take the ratio of area of glucose over area of lactose, which is number 3. That ratio is your Y. And then you can get the concentration of glucose in your sample. Please ask questions and then we have a minute or two. If you want me to repeat anything about internal and external.
When preparing that experiment, it's always the same amount of lactose to like your 15
Everything.
samples. You don't not do it.
The same concentration to correct for any experimental error that was subjected to everything in your solution.
Mhm.
So it's same concentration, same volume of the solution goes into everything. Your experiment standard and no. Yes,
So, using an internal standard, that's an example of like spiking.
no.
No.
Spiking is when you have, you do the so in the decaf sample, you had those three peaks that were very close to each other where caffeine should be. Done now, I probably don't remember, but, here. You have them, where did I draw it? I don't know. Let's say you have them here, 3, 4 peaks in where the standard should come up, where caffeine should come up. And you don't have a photodiode detector, which is a fingerprint. You only have a regular absorption detector. So you don't know which one is taken. You go and in the sample, you add a standard to the sample. That's not an inference. And then the caffeine peak will increase in the size. Yeah. Yeah. It's different than, you are spiking with an internal standard. But you can spike with the actual component to see where it is, to know where it is if the detector is not strong. Or
Just to be real clear, the internal standard is not in the product.
not in the
It's
product
used for data cap correction.
for correction due to experimental error when you're preparing the sample.
And then the external standard is in the product,
Yes,
but we use it for analysis calibration.
to reduce the standard curve. Yeah. Yeah, it's external because glucose not in your sample, you buy pure glucose in fair concentrations.
It just seems about something.
I know, I will post this online, and if you have more questions, I can answer when I see you next, but Gary for sure will start this Friday. Okay, thank you for your patience.
Good.